Industry valve brochures talk about non-slam, non-return valves. How do project teams achieve non-slam or appropriate non-return valve designs? The simple answer is by selecting a non-return valve type that matches the system's dynamics, similar to the way that a pump's lift curve is selected to match a system's head loss curve. We have previously looked at the results of watt-amp simulations to reveal an example system's dynamics and the consequences of a non-return valve closing against a particular maximum reverse velocity. By matching the non-return valve to the system, we aim to select a valve that closes before the system generates unacceptably high reverse velocities. To close in a very small fraction of a second, a non-return valve must have a short valve stroke, that is, a gate that moves over a very small distance, low mass in its moving parts, low internal friction, and spring-assisted closure. There is a wide range of non-return valve types available, some that can close rapidly and some that can't. The first step is for the project team to specify the design limit for maximum reverse velocity, either explicitly or from the client's mechanical design standards. By explicitly, I mean performing a range of transient analyses, similar to those shown in the previous lesson. The aim being to understand the size of reverse velocities the system can generate, the fluid deceleration rates the system can create, plus the consequences of non-return valve closure against various reverse velocities. In the absence of values relevant to a specific engineering project, this lesson presents the subject in qualitative and subjective terms. On the left side of the graph is a scale of reverse non-return valve velocities. The scale suggests that above 0.3 meters per second, severe slam will occur. The previous lesson tended to confirm this. It all depends on what the project client deems to be acceptable or severe. The scale suggests that mild slam is the range when a valve closes against a reverse velocity of 0.15 to 0.3 meters per second. Non-slam is reserved for cases closing against a reverse velocity about 0.15 meters per second. For discussion's sake, let's assume transient analysis has set the acceptable maximum reverse velocity as 0.29 meters per second. So here we have started by specifying a design target for the maximum acceptable reverse velocity, 0.29 meters per second. At the same time, these transient scenarios should have identified the maximum closure time that can be tolerated to keep the maximum reverse velocity below the design target. Let's assume the analyses identified 0.3 seconds as the maximum closure time. The other associated step is to determine the scenarios that could generate the worst deceleration of the water column. These are likely to be pump power failure or stopping one pump while other parallel pumps continue to run. For discussion's sake, let's assume transient analysis has simulated these scenarios and identified the worst deceleration rate as 4 meters per second squared. We may wish that our engineering task will now be as simple as plotting the maximum reverse velocity of 0.29 meters per second and the worst deceleration of 4 meters per second squared on a graph, and the graph will point us to the appropriate non-return valve type. Well, the safest engineering approach is to consider that there is no such reliable graph. Some conceptual graphs have been published, yet we should treat them as only being suitable for suggesting the qualitative relativities between the various types of non-return valves. Plus, we should then accept that not all valve suppliers agree with the relativities depicted on such graphs. So what is the preferred engineering approach? It's to develop a valve specification stating the parameters discovered by transient analysis. 1. Maximum reverse velocity acceptable. 2. maximum closure time acceptable, and 3, the system deceleration rate. Then work with suppliers who can offer non-return valves that satisfy the specification. Having made that recommendation, I will talk through the qualitative relativities between various types of non-return valves, not to give you a valve selection tool, but to help you understand how and why the various types perform differently. This slide examines the various types of non-return valves, their mechanical formats, and compares them in terms of their dynamic characteristics. Valves with poor dynamic characteristics appear on the left side of the graph, and dynamic characteristics improve towards the right side of the graph. We begin with a ball valve. These have a buoyant ball that is lifted out of the way by forward flow, and the ball falls back against the valve seat when flow reverses. A ball valve has a relatively high moving mass and relatively long stroke. Only hydraulic forces and gravity act to make the ball close. Swing check valves are the bread and butter workhorses used in most water supply systems. They are built with a rigid gate hinged at the top. Forward flow lifts the gate. The gate falls back against the seat with reverse flow. Again, a relatively high moving mass and a long stroke. The next improvement in non-return valve design is the resilient hinge format. These valves have a hinge that progressively flexes during forward flow. The bending force built up in the hinge helps the gate to progressively lower against reverse flow. Their advantage comes from lower moving mass. The tilted disc design still uses a high moving mass, rigid gate. Placing the hinge partway down the body reduces the valve stroke compared to a swing check valve. Dual disc or duo check valves are 2 semicircular discs hinged down the middle with spring assistance behind both discs. Their advantage comes largely from the spring assistance. Add a spring at the back of a resilient hinge valve's gate and you further improve their dynamic characteristics. The final format is the nozzle check valve. The concept is a gate or nose that sits at the front of a torpedo-like spring enclosure. In the diagram, the torpedo-shaped enclosure is not shown, neither is the rounded nose shape. The gate moves over a short stroke, has low moving mass, and various spring strengths can be installed behind the gate. How then does a project team select an appropriate non-return valve from this range? Start by specifying a design target for the maximum acceptable reverse velocity. Next, determine the scenarios that will generate the worst deceleration of the water column. These are likely to be pump power failure or stopping one pump while other parallel pumps continue to run. Simulate these scenarios to quantify the deceleration that the system generates, plus the maximum valve closure time that can be accepted without exceeding the velocity limit. Present these parameters to a range of valve suppliers and let them select valves that can be offered to meet these specifications. Thanks for watching. Now please take a few minutes to test your understanding of the subject and review how the lesson has advanced your knowledge.